Okay, we're going to continue on here, chapter 9, maybe we'll go with that. So last time here in this chapter, we were putting together really a few things that we learned in some previous chapters, balancing equation, grams to moles, and we're able to do some calculations from the equations, which is known as stoichiometry. So we talked about really basic stoichiometry problems. And remember, as we talked about, there's pretty much 4 basic steps for stoichiometry problems. You want to make sure you have a balanced equation. And remember, as we talked about, pretty much none of the stoichiometry calculations work if that equation is not balanced, because the basis of stoichiometry is essentially the mole-to-mole relationship that you get from the balanced equation. And remember that that sort of mole-to-mole relationship comes from the balance equation, where we take the coefficients from the balance equation, and that's sort of our mole-to-mole relationship. So we can say that for every 2 moles of A, we get out, for example, 3 moles of C. For every 2 moles of A, we need to react 1 mole of B. And for every 1 mole of B in this example here, we get 3 moles of C. And really, each of those are equal to each other in equality. And as we talked about, they're not equal to each other in terms of numbers, obviously, but they are equal to each other in terms of sort of proportion of those guys that you need for this reaction really to take place. And because they're essentially equality, we could write 2 conversion factors for any of these. So just looking at the first one there, we could really come up with 2 different conversion factors that we could use in a problem. And really, in this particular example here, we could actually have a total of 6 total conversion factors to use in a particular problem. And that really is what stoichiometry is. It's really just a conversion factor. And again, because we can't go to a table to find a relationship between everybody in the equation, we actually use the equation itself as a conversion factor. And that's because usually we're given information about somebody we're not interested in, and we need a way to go from that thing to something else that we are interested in. So everything starts with the balanced equation. And if you don't have these coefficients correct, then all of your calculations are going to be incorrect. The next thing you want to do is take whatever they give you basically and get it to grams, and then take it from grams to moles. And again, thank you. That is the molar mass that we use to do that from the periodic table to go from grams to moles. The reason we do need to do that is because we're going to use the mole-to-mole relationship next. And that's the third step, which is go to the balanced equation and find the mole-to-mole relationship. Obviously, you're interested in whatever they gave you, and you're also interested in what you're trying to find. So that, again, is the 2 things you can do. We also talked about a really important thing about stoichiometry, which is you don't necessarily have to cross the arrow to do the relationships. You could do the relationships with anybody in the equation. You could do it between 2 reactants. You could do the relationship between 2 products. You could do the relationship from reactant to product, or from product to reactant. So it doesn't really matter. You could do it with anybody in the equation. You don't necessarily have to cross the arrow. The 4th step in a basic stoichiometry problem is you should always be in units of moles at this point. You just want to take it to whatever unit it may ask you for. I would say very commonly on the back end of the calculation, we will go to moles back to grams using the molar mass or whatever we're trying to find in that particular problem. So that's a very common sort of back end conversion, is to take those moles back to grams, also using the molar mass at that point. Any questions on any of those steps there? As we also talked about, if something is done for you, just continue on. Don't undo something and, just keep going on in the next step. All right, so now the last time we talked about really basic stoichiometry problems, we're going to talk about a little bit more, I won't say difficult, but a little bit different type of stoichiometry problems. And these are problems that involve what are sometimes referred to as limiting reagents. They're also sometimes referred to as limiting reactants. And when we have a reaction that takes place, the reactants don't always get used up in the same amount. And there's always what is referred to as the limiting reagent or limiting reactant. And what that is essentially the reactant that will get used up first. So when you have a couple of things happening, or two reactants, there's going to be one of them that get used up first. And the importance of the limiting reagent is you need to know which one is the limiting reagent, because if you just think about it logically here, let's say we had a reaction where we had A plus B goes to A and B. And obviously, in this case, you need both of those things to make your product. And let's just say in my example here, this is our limiting reagent. So as soon as A gets used up, is there any chance for me to make any more product at that point? There is no chance. So the importance of the limiting reagent is it is always the one that determines how much product you can make, because as soon as it gets used up, there's no chance that you can make any more product at that point. So when we have a limiting reagent type problem, we do have to sort of take that into consideration. We do have to figure out, which one is the limiting reagent so that we could kind of do our calculation correctly. Now, in addition to the limiting reagent, there's also what is referred to as the excess reagent. And the excess reagent is the one that you have plenty of. So it's the other sort of reagent that you have plenty of. You will actually have some of the excess reagent left over when the reaction is done. So it definitely will not all be used. And a lot of it will be left over when the reaction is completed. So how do you know it is this type of problem? How do you know it's a sort of limiting reagent problem? The easiest way to figure out if it is a limiting reagent problem is, can you get to moles of each of the reactants? So that is pretty much the key. And just the basic of that is you're given info about both reactants. So really what you want to look at is, if you're given information about both reactants, do you have enough information given to you to actually get to moles of both reactants? And if the answer is yes, then you know it's a limiting reagent problem, and you got to take that extra step to figure out which one's the limiting reagent. Now, if you think about a lot of the problems that we did previously last time, if you look back on those problems, what you will see is you're just given like one piece of information, like just one information about one of the reactants. You're not given information about both reactants. So that is the way you could really determine if it is sort of a limiting reagent problem. Any questions on that there? So here, if we're going to make exercise buddies here, we could determine, in this case, obviously we need one of each. So these guys could pair, these guys could pair, these ones here could pair. And as you can see at that point, we are out over here on the right. So on the right-hand side, these guys here are going to be our limiting reagent. On the left-hand side, this is going to be our excess reagent. And also a very common question that's asked in these type of problems is how much of your excess reagent is still left over. So clearly in this simple example here, we can just count and we have 2 left over. So those are very common sort of things in limiting reagent problems that you're asked to find, which is how much product you'll produce, how much of the excess reagent is left over at the end of the reaction. So how do we go about sort of doing these problems? The good news is it's kind of the same steps that we did previously. We just have to do an additional step. Now, I will be honest with you, there are multiple ways that you can do limiting reagent type problems. So I'm going to talk about probably a couple ways, one way, and then I'll kind of talk about the other sort of popular way that you could do these problems. So you can kind of choose whichever way that you want. But just off the top of my head, there's 3 different ways you can kind of do these type of problems, depending on sort of what you choose. So the same sort of steps we're going to follow in these limiting reagent problems. We're still always going to start with a balanced equation. We're still always going to convert to moles. And right around here in the method I'm going to show you, if it is a limiting reagent problem, we will do a calculation to figure out which one is the limiting reagent. And then once we figure out which one's the limiting reagent, we'll just pick up with our steps like normal. We'll do our mole to mole relationship. And then we'll convert those moles to some other unit. So this is sort of the method we're going to kind of talk about here today. And like I said, I'll talk about the other sort of way that you can do it as well as we get going. So let's take a look at an equation such as this, where we have S plus 3F2 goes to SF6. And let's just say, for example, here, I didn't write over everything. So we'll erase what I wrote there. There we go. So let's just say, for example, that we're going to start this experiment or reaction with 4 moles of S and 20 moles of F2. Okay. So first off, the big hint here that this is a limiting reagent problem is clearly I got the moles of each reactant, or I'm able to get to the moles of each reactant. So as soon as you see that you have information about both reactants, and more importantly, that you could get the moles of both reactants, that is the key that this is a limiting reagent type problem. So we're going to start with our first step, which is to balance the equation, which is already done for us. We're going to take our next step, which is convert to moles, which once again, in this particular case, is already done for us, so we don't have to do that. So because we can recognize this as a limiting reagent problem, we're going to now figure out which one is the limiting reagent. So the way that we're going to do this is we're just going to do a very simple calculation between the reactants to figure out is if I want to use up all of my, say, sulfur, how much of the F2 do I need to put in there with it? So this is sort of the limiting reagent calculation here. What I want to know is if I want to use up all of the sulfur, how much of the other reactant, the F2, is needed. So what I'm going to do is take the moles of sulfur, and I'm going to use the stoichiometry between the sulfur and the fluoride, or fluorine here, which is 1 mole of sulfur gives me 3 moles of F2. And I'm going to use that in just a basic little small stoichiometry calculation of 1 mole of sulfur gives me 3 moles of F2. The moles of sulfur will cancel. And that tells me that I need 12 moles of fluorine is needed in this case. So first off, any question on that calculation? It's just a simple little between the two reactants, like I want to use up all of one reactant, how much of the other I need to put in there. At this point, what we just calculated was I need 12 moles of fluorine. And how many moles of fluorine am I starting with? I am starting with 20 moles. So I want to compare how much I need to how many moles I'm starting with. And if I need 12 and I have 20, do I have enough? I do have enough, right? And because I have enough in this case, what that means is the F2 is going to be my excess reagent. And by default, the sulfur here will be my limiting reagent. So that is the big stoichiometry calculation to basically figure out which one is the limiting reagent. You can choose either reactant. So you don't necessarily have to do them both, but I'm just going to show you that if you chose the other reactant, it will come out the same. So for example, if I chose alternatively to figure out the limiting reagent, if I want to use up all of my F2, how much S is needed? So we would start with our 20 moles of F2 in this case. We will use our same mole to mole relationship, which in this case is 3 moles of F2, 1 mole of sulfur. And we'll take 20 divided by 3 gives us about 6.67. So in this case, if I chose the other reactant, I have now calculated that I need 6.67 moles of sulfur. How many moles of sulfur do I have? I only have 4, so I do not have enough in this case, which tells us the same thing, that again, because I do not have enough, the sulfur is going to be my limiting reagent, and by default, the F2 would be my excess reagent. So you could choose either reactant and do this type of calculation to figure out how much of the other reactant you need to use it completely up. And if you have enough, then it's the excess reagent. If you do not have enough, then it is the limiting reagent. Any questions on that there? Okay. So obviously here, do not have enough. So it is our limiting reagent. Okay, so the importance of this calculation is to tell you which one is the limiting reagent. And by the way, a very common mistake that people make is they convert things to moles when they're doing this and go, cool, the smaller number is the limiting reagent. And that is not always the case. So in order to determine which one is the limiting reagent, you have to do some type of calculation to determine it. It's not always going to be the smallest number. It may be, but it won't always be the smallest number. So that's a very common mistake people do, is just kind of convert things to mole and go, okay, that's the smallest number, so I'm going to go with that one. So in order to properly do it, there has to be some type of calculation component to figure out which one is the limiting reagent. Now that I know which one is my limiting reagent, I could really pick up with the remaining steps of my problem, which is I would always want to use the limiting reagent to figure out how much product is going to be made. So at this point, we would go step 3 using our limiting reagent, which is the sulfur in this case. And it's also really important that we use the starting amount for sulfur. So we're not going to really use too much of that calculation there. So we're going to use our 4 moles of sulfur. And now we could do the relationship between sulfur and our product, which is a 1-to-1 relationship. So 1 mole of sulfur gives us 1 mole of SF6. So 1 mole of sulfur, 1 mole of SF6. Moles cancel, gives us 4 moles of SF6. This would be, once again, our theoretical yield in moles. We could obviously use the molar mass at this point and convert it to grams if we wanted it, and it would be the grams of SF6. First off, any question on that? All right, so in addition, the nice thing about doing this method is, for example, if I wanted to know, say, how much of my excess reagent is left over, right? So let's just say I want to know, in addition, how much of my excess reagent is left over. I could actually use this calculation that I did first here, which is I know I need 12 moles of my excess reagent. I know I have 20 moles to start with. So I would take our 20 moles minus it from 12 moles that's necessary, which would leave me about 8 moles of my excess reagent left over, which once again, I could use the molar mass of F2 and figure out how many grams that would be as well. So the benefit of doing it this way is, if you're asked that question of how much excess reagent is left over, you can, if you sort of pick right, kind of do that calculation really quickly as well. Any questions on that there? So the other very common method to figure out limiting reagents is, frankly, to do this. So the other very common method is, we had was 4 moles, I think, right? And 20 moles, right? So the very other common method to figure out limiting reagent is just to do 2 different stoichiometry problems, where you take the moles, say here, of sulfur, you do the mole to mole relationship between sulfur and your product. And if you want, you could also use the molar mass here. And that will give you grams of SF6. Then you would do a second calculation with the other reactant, which would be 20 moles of F2. It'd be 3 moles of F2 to 1 mole of SF6. And you use the molar mass of SF6 here, grams of SF6. And you basically just do two separate calculations, and whichever one is the smallest number of grams will be your limiting reagent and your theoretical yield. So that is the other very common method. It's just to do just two separate calculations, one from each reactant going to the product of choice, and whichever one gives you the smaller amount of grams is both your limiting reagent and your theoretical yield. So that is a very common way of doing these type of problems. So whichever method you like, it's okay. I will say that if you do have a question like how much excess is left over, you will have to kind of go back and do some other calculations anyways. So, it is just your choice. You could also compare moles as well, whichever gives a small number of moles of each product will do it. So that is the other very common sort of method of doing these problems. Any questions on either method here? All right. So let's take a look at one here, I think. Maybe. There we go. All right, so why don't you give this a go? We have 6.83 grams of iron are allowed to react with 9.34 grams of sulfur, which is the limiting reagent, and how much FeS will be formed. Iron is 5585. Sulfur is a 3207. Yeah. So again, follow. Okay, let's take a look and see how you're doing. So once again, we're going to approach this like a stoichiometry problem. We have a balanced equation, so that's good. We are given 6.83 grams of iron and 9.34 grams of sulfur. We are given enough information for both reactants that we could get to moles of both of those guys. And that is the key, that this is going to be a limiting reagent problem, because again, we are given information about both reactants and we could definitely get to moles of both of those guys. So that is really the key of how you have to do this sort of additional step along the way. Regardless of what method you choose to do this, the second step is usually the same. You got to convert everybody into moles, which we do need to do in this case. So we will convert our 6.83 grams of iron. Using a molar mass of iron there from the periodic table, 5585 grams per mole. And that's going to get us here 6.83 divided by 55.85. We'll call it 0.122 moles. We'll also do the same thing here for our other reactant, which is our sulfur, 9.34 grams of sulfur, using the molar mass of sulfur from the periodic table, 3207 grams per mole. So this will give us 9.34 divided by 32.07. That's going to give us 0.291 here. So once again, this is sort of step number 2. This is also our starting amount of each of these guys. Any questions on that so far? So because we did recognize it as a limiting reagent problem, I'm going to do my limiting reagent calculation here, which means once again, I'm going to choose either reactant. It doesn't matter which one you choose. I'm going to choose the iron. So I want to use up all my iron. How much sulfur is needed is basically this calculation. So we'll take the moles of my iron, which is 0.122 moles. We'll go to the equation and we see that for every 1 mole of iron, we get 1 mole of sulfur. So that's our stoichiometry relationship. So we're going to use that there. 1 mole of iron, 1 mole of sulfur. That means 0.122 moles of sulfur is needed. Once again, we're going to take that of how much we need and we're going to compare it to how much we're starting with. And do I have enough in this case? I do, right? I only need 0.122 moles and I have 0.29 moles. So we have enough. And what that means is the sulfur here is going to be our excess reagent. And really the nice thing about this is as soon as you determine which one's your excess reagent, by default, the other one would be your limiting reagent. So you really only have to figure out one of them. And by default, the other guy is the other sort of reagent. Any questions on that determination there? Okay, so now that I've determined which one's my limiting reagent, we want to make sure that we go back now and continue on with our calculation. But we do want to make sure that we, for step number 3, go back and use the starting amount here of our limiting reagent. So we're going to then do step number 3, which is 0.122 moles of iron. We're now going to use our limiting reagent to figure out how much of our product we will make. 1 mole of iron gives us 1 mole of iron 2 sulfide from the equation. Gives us 0.122 moles of iron 2 sulfide. Lastly, here we're looking for how many grams. So we will use the molar mass of these two. So we'll just add them together. And that will get us 5585 plus 3207, 87.92. So using that as our final conversion factor here, grams up on top so that we end up with grams, moles on the bottom so they cancel, will get us here about 10.7 grams of FES. This would be our theoretical yield in this case, as it is a product. Any question on those steps there? Now, once again, we could very easily, if we were also asked to do so, which we were not obviously in this question, but we could very easily figure out how much of our excess reagent was left over. And once again, we could use our calculation that we used for our limiting reagent. We know that we needed, in terms of our excess reagent left over, we needed 0.122 and we started with 0.291 moles minus 0.122 moles will give us about 0.169 moles of sulfur left over, which we then can multiply by the molar mass of sulfur, 32.07 grams per mole. Is about 5.42 grams. So we started with 9.34 grams, and in this reaction, we used about 4 grams, just under 4 grams of it to do this reaction, and we still had about 5.42 grams of it left over. So again, that's also a very common question that's asked, which is how much of that excess reagent is left over. Any questions on any of those steps there? Okay, so let's try another one here in C. It's good they agree. All right. There we go. All right, so let's try this one here, see what you come up with. Here we go. All right, in this reaction, you go out 622.7 grams of ammonia. The molar mass from the periodic table, 1703, is react with 1241 grams of CO2, molar mass, that given to you. Which one is the limiting reagent? And how much product would you produce there? And also how much of the excess reagent will be left over. So take a few moments there, see what you come up with. Okay, let's take a look and see how you're doing. So once again, we have this problem here. We're looking for how much product. We're looking for how much of the excess reagents left over. Clearly, we do know it's a limiting reagent problem, but once again, if it was not given to you, like give the excess reagent and all that, the way you would recognize it's a limiting reagent problem is you have grams of both of the reactants. And really, again, what that means is you're able to get to moles of both of those guys. So it definitely is a limiting reagent problem. So again, whenever you have enough information given to you in the problem that you could get to moles of each reactant, then it definitely is a limiting reagent problem. You have to kind of do that extra step. So in this case, we're going to balance the equation, which already is. We're going to convert to moles, which we do need to do here. So we'll take our 622.7 grams of NH3. They were nice enough to give us the molar mass. If not, you would have to go to the periodic table, obviously, and calculate that yourself. 1703 grams per mole. And that's going to give us here 622.7 divided by 1703, about 3656, we'll call it. We are going to do the same thing here for our other guy. So 1241 grams of CO2. Once again, using the molar mass that they gave us, 4401 grams per mole. And obviously, just like the other one, you would have to go to periodic table if it was not given to you. Going to get us, we'll call it 2820, we'll call it. So again, any questions on that? That's basically just like any other stoichiometry problem. If it helps you, you could label this as like your starting amount, basically. So you remember that that's what you want to use to compare. Now we have to do our limiting reagent type of calculation. So once again, I'm going to grab either reactant. So I'm going to just figure out how much CO2 is needed. Is needed to use up all of the NH3. So that's the little calculation I'm going to do right now. So I'm going to take the moles of my NH3 I'm starting with. I'm going to do the mole to mole relationship from the equation between the NH3 and the CO2. And from that, that is 2 moles of NH3 gives me 1 mole of CO2. So using that as our conversion factor here, we're going to be able to figure out how much CO2 we need. That we want to go on the top, and our 2 moles of NH3 on the bottom. NH3 will cancel, and this will give us 3656, basically divided by 2, 1828. And again, that is how many moles of CO2 is needed. We want to then compare it to how many moles we're starting with, and do we have enough in this case? We do, right? So we only need 18. We got about 28. So we have enough. And again, once you identify one of them, which means that this guy would be my excess reagent, this in this case here would then be my limiting reagent. Any questions on that? Yeah. No, you will not. So for example, if you chose the other way of doing it, which is how much NH3 you need to use up your CO2, you would find out that you did not have enough. So you can choose either one. They both will tell you the same thing in terms of which ones you're limiting and which ones you're excess. But just so happens I picked this one, and again, we had enough, but it may not always be that. So if you do not have enough, it just means that thing would be your limiting reagent. Other questions? All right. Also, a good note here, right? It is actually the larger number, right? Is the limiting reagent, right? Not the smaller. So again, you have to do some type of calculation to figure it out. Now that we know which ones are limiting reagent, really at this point, it just falls back to a normal stoichiometry problem. So we're going to go with our limiting reagent, which is our 36.56 moles of NH3. And we're now going to go from our limiting reagent to our product. So we want that relationship there, which is 2 moles of NH3 gives us 1 mole of our product here. So using that, 2 moles of NH3, 1 mole of our product will get us 18.28 moles of our product. And lastly, in this case, we're not looking for moles of our product, but we are looking for grams. So we will do our 4th step, which is 18.28 moles of our product. Once again, if it was not given to you to the periodic table, you would go to figure out the molar mass. But in this case, it was given to you as 60.06 grams per mole. Those will cancel. And we'll times that by 60.06. Looks like 1098 grams of our product here. And in this particular case, that probably looks good. We got 4 sig figs on everybody, so we'll go with that. This would be, again, our theoretical yield in this case. Any questions on that there? The other part of the question was how much of our excess reagent would be left over. So in this case, we got excess left over. So because we chose kind of correctly here, we already know how much of our excess reagent we need. And we know how much we started with. So we started with 28.2 moles of CO2. How much we started with. We need to use 18.28 moles of it. That's how much is needed. And that would get us 28.2 minus 18.28, 9.92 moles of CO2, which we could use the molar mass of CO2, which was given to us, times it by 4401, and about 436.6 is left over. So we started with about 1,200 or so grams of the CO2. In this reaction, we will use about 600, 700, 800 grams or so, and we'll have 400 of it left over. Any question on that? Now, if you by some chance did not choose the calculation I did here, and you chose the other calculation where you figured out how much NH3 you needed to use up all your CO2, you would then have to go back, obviously, to answer the last question and kind of do that calculation to figure out how much of your excess reagent was needed. So sometimes you get lucky and you do sort of choose the right one to answer that question, but in case you didn't, you would have to go back and basically just do the other calculation here, and then that would allow you to kind of do this if you chose the other way. Any questions on any of those steps there? Okay, so let us continue on then. Good, it has the right answers. That's good. All right, so next thing we're going to talk about are yields of reactions. We started been touching a little bit upon some of the yields here. A yield is always, by the way, going to be a product. So it has to be a product really to be a yield. And that's really what the arrow means, to yield whatever's on the product side. So there's a few different types of yields. So let's talk about them here. First off, there is the theoretical yield. And the theoretical yield is pretty much what we've been calculating. It is the maximum amount of product that you should produce in that reaction if like everything went perfect. There was, again, no side reactions. You didn't spill anything. You didn't lose anything along the way. Based on the equation, based on the stoichiometry of the equation, and based on how much reactants you're starting with, That should be your maximum amount of product that you should actually produce in this reaction. Again, if everything went perfect. Unfortunately, everything doesn't usually go perfect. And as you'll see probably this week in lab, you can't always scrape out everything out of a test tube that you make. So some things are sometimes left behind. So what that brings us is the other important yield, which is the actual yield. And much like the name implies, it is actually the amount of product that you made when you did the reaction, basically. So it's actually how much product that you produce. The actual yield should always be smaller than the theoretical yield if you didn't screw up. Now, in real life, you might actually have an actual yield higher than the theoretical yield, which means you screwed up somewhere probably. But in reality, it should actually be lower. But if you do find yourself with a actual yield higher than a theoretical yield, then something probably did go wrong in your experiment when you're doing it. Taking both of these yields together gives us the one that we're kind of important about when we do an actual equation or reaction is what's known as the percent yield. And the percent yield is the actual yield divided by the theoretical yield times 100%. The good thing in textbook problems is this is usually given to you. So somewhere in the problem, they'll tell you how much product that you produce. This is usually something that you need to calculate. And that calculation may be just a basic stoichiometry problem. It may be a limiting reagent problem. So one of the two ways you need to calculate your theoretical yield. Ideally, we want a high percent yield. High percent yield means we did it pretty well. A low percent yield means you did pretty bad. Can you get over 100% yield? The answer is, in reality, yes, but it also means you screwed up. Yeah, so you shouldn't really technically get over 100% yield. Again, you might have made a mistake. A very common way that sometimes people do get like over 100% yield, like you're going to do, I think this week, is you're going to do like a precipitation reaction, and you take this precipitate and you filter it through onto a filter paper. And as you know from filtering some things before, perhaps, if you filter it there, that filter paper is going to be wet. And if you don't let it completely dry and you reweigh it too soon, you're getting a lot of water weight that you're counting as your product, but it really is not. It's just the water, right, weight that you got there because it wasn't dry. So that's a very common place that people can sometimes go over 100% yield is they don't let their product really dry before they reweigh it at the end of the experiment. And as you do it, you're basically collecting more water weight than you really should have. All right, so let's try one here, shall we? Give it a go. We got 2.46 grams of TiCl4. Molar mass from the periodic table, 189.7 grams per mole. Reacts with 1.44 times 10 to the 4 kilograms of magnesium, molar mass 24.31. What is the theoretical yield of Ti? And what is the percent yield if we produce 5.42 times 10 to the 3 kilograms? And Ti by itself, 47.88. Yeah, let's take a look here and see if this one with some big numbers. There we go. All right, so obviously we are starting with some kilograms of each of the reactants. Although they are in kilograms, it doesn't really matter because I know hopefully we could get the grams, and that also means we could get some moles of each of the reactants. So once again, because of that, that does tell you that this is a limiting reagent type of problem, and you do have to at some point figure out the limiting reagent. All right, so we'll just kind of roll through our steps. The first two steps are the same no matter what method you choose. We want a balanced equation, which it already is. We do want to convert to moles, which we do need to do. So here we'll start with the TiCl4. We have 2.46 times 10 to the 4 kilograms. We do need to convert it to grams first. So kilograms, 1,000 grams will do that. Now we could use the molar mass from the periodic table, or what they gave us actually. So you didn't have to actually look it up, so that's good. And now we are not in moles because I did it backwards, but if I wrote it correctly, that would be good. Try that again. There we go. All right, so we want our grams on the bottom so they cancel, and moles there up on top. There we go. Grams cancel, and that gets us here for our TiCl4. Make sure you use your exponent button times 1,000 and divided by 189.7. Looks like I'll call it 1.30 times 10 to the 5. We're going to do basically the same calculation here for our other reactant. So we got our moles of magnesium, 1.44 times 10 to the 4th kilograms. Once again, we're going to convert it into grams. So 1 kilogram is 1,000 grams. Now we could use the molar mass correctly here. So we'll go with 2431 grams per mole. Grams will cancel. 1.44 to the 4th times 1,000 divided by 2431 gets us 5.92 to the 5th here. And once again, these are your starting amounts of each of these. Any questions so far? All right, so now like normal here, we're going to do our little limiting reagent calculation. So I'm going to figure out how much magnesium is needed to use up all the TiCl4. So I'm going to take the moles of my TiCl4, which is our 1.30 times 10 to the 5th. We're going to go to the equation and find the relationship, the mole-to-mole relationship between those two. And we can see that for every 1 mole of TiCl4, we get 2 moles of magnesium. So that's what we're going to use as our conversion factor here. 1 mole of TiCl4, 2 moles of magnesium. Those guys will cancel. Going to get us here 1.3 to the 5th times 2. 2.60 times 10 to the 5th moles of magnesium is needed. So here in this case, we're going to look and we see that we do have enough in this case. And again, you won't always have enough, but in this case, we actually chose okay. So that means that the magnesium is the excess reagent. That would then mean that our TiCl4 is our limiting reagent. Any question on that calculation? Now that we've determined the limiting reagent, it is always the one that determines how much product we're going to make. So we will use our starting amount of our limiting reagent here. We're going to use our starting amount of our limiting reagent to figure out how much product is going to be produced, which is kind of like our third step in our stoichiometry move. That's like our second step. So we'll take our 1.30 times 10 to the 5th moles of TiCl4. Now we want the relationship between our limiting reagent and our product, which happens to be a 1-to-1 relationship. 1 mole of TiCl4 gives me 1 mole of Ti. So that's not too bad. And if I stop right at this point, I am in moles of Ti, which if you want an answer would obviously in this case be the same number. And now we can convert the moles of Ti into grams by using the molar mass here. But our actual yield here, right, is in kilograms, which means we probably also want to then convert it into kilograms. So everything's the same. So 1,000 grams in a kilogram, just to get everybody in the right units. So we're going to take 1.3 to the fifth times 4788 times, not times, divided by 1,000. Going to give us 6.22 times 10 to the 3 kilograms, as I did the kilogram conversion there, TI. This would be our theoretical yield. Yeah. First off, any question on that part of the calculation there? At this point, we can now calculate our percent yield because we have everything that we need. Percent yield would be our actual divided by the theoretical times 100%. Once again, the actual was given to us in the actual problem. It said that we produced 5.42 times 10 to the 3 kilograms. We just calculated our theoretical, 6.22 times 10 to the 3 kilograms times 100%. And that's going to give us a percent yield in this case of about 8708, I guess. Not terrible. Percent yield. Yeah. What's that? Why do you need to do the red part? You do need to do the red part because even though they do not ask you, which is very common, it is a limiting reagent problem. So they won't always in the question go, hey, it's a limiting reagent problem. And that's why I've been saying that if you see a problem where you're given enough information about both reactants that you could convert it into moles for each of them, that is the key that it's a limiting reagent problem. So they definitely will not always tell you it is. What's that? Yes, because it's the limiting reagent that determines how much product did you make. So you need to determine which one is to do this part of the calculation. This part of the calculation is based off of that guy being the limiting reagent. And if you don't know which one it is, you might choose the wrong one, right? So you have to do it. And again, that is definitely the key way. If you're given enough information from both reactants, you could get to moles of both reactants from the information given to you. Definitely a limiting reagent problem. You need to do that. And that's always the one that's going to determine how much product you make. Other questions on that? Yeah.
Where does step 4 start?
Where's the 4 start? Step number 4? Step number 4 would be right here. This would be step number 4. Is that what you're asking?
Yes.
Yeah. I just took one more part of that step because we needed it in kilograms. So I just did the extra kilograms part, but I'm putting my hand over here like it's going to go on the screen. But if you put your hand over that last part there, that's basically just converted into some other unit, which is the 4th step. Yeah. Now, speaking of percent yield, also, just so you know, it doesn't matter the units. They just need to be the same units, the actual and the theoretical. So although we did kilograms and kilograms here, you could do grams and grams, you could do moles and moles, as long as the actual yield and the theoretical yield are in the same units. It doesn't really matter what units they are. You could calculate the percent yield from them. Question on that? All right.